Okay, I'm going to get started. So this class will be on exploration. So what is the exploration problem? The word exploration is used to mean several different things. In fact, it's sometimes abused a little bit. So there's an older meaning of the term, or there's a more precise meaning that has to do with what's called the exploration-exploitation problem. So the way you can sum this up is you say, say you have a long-lived agent. How do you balance exploration and exploitation, meaning use what you know to get as much reward as possible in the near future, or try to gather more information in order to maximize long-term rewards. And the term exploration also has a more informal meaning. It's used to refer to methods for avoiding getting stuck in local optima of behavior. So it's used to refer to methods that try to search over different behaviors to find, so it doesn't get stuck prematurely in a local optimum. So I actually liked I was looking at Dave Silver's slides on the exploration problem, and I liked his slide on this topic, so I've just reproduced it here. So just as some examples of the exploration and exploitation problem, so the problem is informally whether to just use what you know right now to maximize short-term reward, or try to gather more information which will pay off in the future. So you can see some examples here of exploration versus exploitation decisions you might make in different real-world applications. Okay, so there are several different settings I'm going to cover in this class. And basically, there are several different settings you can use to study sequential decision problems. And they range from problem settings that are theoretically tractable but kind of simplified, and problem settings that are hard and sort of and general, but hard to say anything formal about. So on the theoretical end, we have the multi-arm bandit problem, where you can basically there's a very nice theory that says what's optimal, and you prove lower and upper bounds on everything, and you show that your algorithm is optimal. So that exists in the bandit setting. Then there's this contextual bandit setting, which is sort of in between the bandit setting and the MDP setting, which I'll briefly mention but won't go into much. Then we'll talk a little bit about the setting of finite MDPs. That means finite state and action space, where you can actually prove something about algorithms that are near optimal when you run the algorithm on a previously unknown random MDP, that it'll find a near optimal policy in some finite time. And then the setting we're kind of most interested in for deep reinforcement learning, or for empirically driven research, or for various kinds of applications, is where you have a large or infinite MDP, and you're running some kind of online policy gradient or approximate dynamic programming algorithm with function approximation. So there it's theoretically intractable, but we can still develop heuristic methods. And actually the nice thing is that when you look at the settings, the simplified settings that are amenable to theory, a bunch of different classes of algorithms have come out, and a bunch of different insights have come about. And it turns out that a bunch of these insights can be used to inspire algorithms that apply in the hard intractable setting. So in particular, one class of algorithms for bandit problems is based on the idea of optimism, where you're uncertain about how good all the different actions are, but you're optimistic about the values, and you use that to choose the action. So you favor uncertain actions that have uncertain results. So that's one approach, and Another approach is what's called Thompson sampling, which we'll go into later. But anyway, both of these ideas can be applied in the more intractable and the other settings where we don't have a theory. But anyway, I'll go into the details shortly. This is just sort of an outline. So first let's just go over the bandit problems. So bandit actually in sort of archaic terminology, it means a slot machine. And the idea is you want to choose, the slot machine gives you random returns when you put quarters into it. And you want to find the slot machine that gives you the best results. And of course, this doesn't totally make sense because usually slot machines all have negative returns. So it's not a very good way to make money. But that's just how the problem is described. And it's sort of, it captures the stochasticity. So to be a little more formal, let's say in the bandit problem, we say there are k arms, which are k actions. And we have n rounds, in which we're going to choose actions. And we don't know what the returns are for each action. So for each action, there's a probability, p of reward given action. But we don't know what these these probability distributions. And so the process that the agent goes through is every time step, the agent chooses an action, and then the environment samples a reward according to this distribution, depending on that action. And our goal is we want to maximize the cumulative reward obtained by the agent, the expected cumulative reward, which is equivalent to minimizing regret, which is just your cumulative suboptimality of the actions you take. So actually, so Ian Osband made a really nice little JavaScript program that demonstrates the bandit problem. So I want to show you this problem and explain, as a way of explaining the bandit problem. Does anyone want to volunteer from the audience to compete against the bandit algorithms in a decision-making problem? So here, Ian has a very colorful blog. I recommend it. So the way I'll first describe the problem so you know what you're getting into if you volunteer. So in this problem, it's considering the application is just discovering which treatment is best. If there are multiple different drugs and they all have different success rates, and you have a bunch of patients that you can give different treatments, and you want to figure out which one is the best. So then you see there's an exploration-exploitation problem because first you have to give random treatments to a bunch of patients to figure out which one is the best. And then once you've sort of settled on which one to use, then you should give that to all future patients to minimize how many people you're giving the wrong treatment. So that's a pretty clear application where you want to minimize the amount of harm you're doing, and you have to decide what treatment to give everyone. Or I shouldn't say minimize harm. You want to maximize the benefit to them. So anyway, in this setting, there are 4 different drugs, and we're going to say there are 40 patients. And each patient that comes along, you have to decide what treatment to give them, and then you just figure out, then you see if it was successful or not. Does anyone want to volunteer? Come on. Sergey?
How about drug 1?
Okay. Patient lives, see?
Okay, well, that's what we want, right?
Yeah.
Okay, well, let's do that again.
Okay.
Okay, great. Now let's do it forever.
Oh, you want to do that one the whole time? Okay, that's one strategy. Okay, let's see what happens. I'll go with it.
He died once. Pretty good. So the best exploration algorithm is Problem solved.
Okay, so let's see what happens. Oh, so actually, it turns out, so now we see what the true efficacy was. So it turns out drug 1 was 90% effective, drug 2 was 70%, drug 3 was really bad, and drug 4 was actually the best. So Sergey picked a near optimal action. Okay, so now let's look at how many lives saved. So let's see, does it say, okay, Sergey is purple. Okay, so Sergey actually did pretty optimally.
Yeah, my greed has cost 1 life.
So actually the funny thing is epsilon greedy here. So the epsilon greedy algorithm is in this, well, I don't know exactly how they set it up in this particular applet, but it would be something like you choose all of the actions once to get an initial value of the mean reward, and then you keep choosing the one with the highest mean. Except with probability epsilon, oh, actually, maybe they don't forget about the initialization. So they're just going to choose with probability epsilon, they'll choose a random action, and with probability 1 minus epsilon, they'll just choose the one with the highest mean. So that's epsilon greedy. That's one strategy. And then there are a few other algorithms, some of which I'll talk about later. But the idea of minimizing regret is, let's say we look at what's the performance of your algorithm. I mean, how good are the actions being chosen by your algorithm versus the best action. So we have a best action, which is max over A of Q of A. And so let's call that Q star. And then the suboptimality of your action is Q of A, or Q star minus Q of A. Say you're trying to maximize the reward. So this is the suboptimality at time t. So your total suboptimality is just your sum over t. Or let's just say sum from t equals 1 to n of this. So what you might find over time is, let's say you just have the wrong, if you just choose the wrong action and stick with it, like Sergey did, this is called your regret. So your regret is going to just go up linearly. So the regret turned out not to be very large in this case because the action, Sergey's action, was only slightly worse than the best action. But if you do this, your regret is going to go up linearly. So this is regret after n steps. So what we really want is an algorithm where the regret is sublinear, so it'll look like this. And that's what bandit algorithms seek to do. They try to find they try to make the regret grow as slowly as possible. And it's impossible to make the regret totally to make it bounded as time goes to infinity, because you might have just gotten a really anomalous set of results for all previous time steps. So if you were to I mean, the only way to have finite regret is if you stick to a single action after a while. So after n steps, you have to stick to a certain action and never take another one. That can always be suboptimal because you might have just gotten a really anomalous set of outcomes at the beginning, and then which will cause you to choose the wrong action, and then you're going to end up with linear regret, linearly increasing regret. Okay, so now I'm just going to talk about some different methods of approaching bandit problems, all of which are going to actually extend to the more difficult settings like the MDP setting. So one way to view them is to look at the bandit problem as a POMDP. So this is sort of this is one ideal way of solving the problem. So let's say you have a prior on the parameters of the problem. So let's say each bandit is, well, each bandit gives you a probability distribution over possible returns you're going to get if you choose that action. So for example, in the medical treatment case, each one is a Bernoulli distribution, meaning there's a certain probability of the patient lives or dies. So you have let's say you have a prior distribution. You have a prior on all those Bernoulli parameters. So now you want to figure out what's the optimal sequence of actions to take. And you can actually view this problem as a POM-DP. So note that in the bandit problem, you have an environment that isn't stateful, meaning if you take an action at time t, the result doesn't depend on what you did at time t minus 1. However, your belief state is something that gets updated over time. So that means your distribution, your probability distribution over the problem parameters, that's something that gets updated over time. So the way we turn this into a POM-DP is we say that the state of our system is the history of all actions and rewards we've gotten so far, which is going to determine our posterior probability over the problem parameters. And so the bandit itself isn't stateful, but our belief state is the stateful part. It turns out that, well, there's this surprising result that if you consider the discounted problem, well, and actually I think there's also an analogous result for the undiscounted finite horizon case. There's this result called the Giddens index theorem, which says that we don't actually have to, I mean, this would seem like a really high, actually let me go back a step. So does everyone understand why this is a POM-DP? Okay, so now that we know it's a POM-DP, we could theoretically solve it using dynamic programming. So we could say, let's say it's a finite horizon problem with 10 steps. We could just do dynamic programming backwards in time to figure out what's the optimal policy at each of these time steps. But we have a state space that's exponentially large in the time horizon because our state consists of our whole history. So we have a really big state, and this is impractical, even in this finite bandit case. So that's not such a practical solution. And it turns out there's this remarkable Giddens index theorem, which says that you only have to compute a certain quantity for each bandit separately without knowing anything about the other bandits. And then you choose the bandit with the highest Giddens index. So that's a pretty nice result. And people were pretty excited about this when they saw the result. Unfortunately, well, there are a couple of limitations of it. First of all, it assumes you're in this Bayesian setting where you have a prior distribution on everything, and it doesn't necessarily provide a good guarantee if your prior is wrong, or if your prior doesn't, if your prior doesn't match with the actual prior distribution. It also doesn't extend very well to the more difficult settings. So this Giddens index result only really holds in a particular finite bandit setting, or it doesn't yield useful algorithms in the other settings.
Question.
Yeah.
So in an infinite setting, how does that help me with the exploration? Because if I need a prior, then I would first of all sample the environment a lot of times to get these priors, right? And then I'm stuck with another exploration problem. Like how am I going to get this prior?
Okay, so the question is, how do you get the prior distribution? Well, that's sort of a fundamental question in statistics that doesn't really have a universal answer. The prior is just, if you only have are solving one problem, then you have no way of choosing this prior. You just have to choose it based on what you know about the universe. If you have many problems, then the prior distribution, then you could try to fit a prior somehow. If you're solving if you're solving a sequence of different bandit problems, then you could try to fit some distribution to the parameters you're getting and use that as a prior for if you're given a new problem. Okay, so now that brings us to another class of algorithms, which are based on the idea of optimism in the face of uncertainty. And in particular, there's the abbreviation UCB, which stands for Upper Confidence Bound, not UC Berkeley. The idea is let's say you're in this bandit problem. For each arm, you've chosen that arm a certain number of times, and you've gotten a certain mean return from that arm. So you'd like to choose the arms that both have high rewards and also have high uncertainty, or the ones that have been chosen fewer times, because those might end up turning out to being good. So let's say, I mean, if you've chosen a given arm many, many times, then you presumably have low uncertainty on its returns. So just to illustrate this a little bit, let's say we draw a little histogram which shows on our 3 actions, we have a certain mean return for each of those actions, and then we have a certain uncertainty, which I'll draw as this error bar. Then ideally, we'd like to choose the actions that have a high mean and also a big error bar, because those ones might turn out to be good. So in the original UCB algorithm, it actually doesn't look at the standard deviation. It doesn't look at any kind of standard deviation of the returns. You choose the arm that has the highest value of mean of this arm. Let's say mean sub A plus something like 1 over it's 1 over square root of number of times you've chosen that arm. And actually, there's another factor. So you have a factor that's like log of n, which is the total number of steps so far. Anyway, this is so you're choosing mean plus something like 1 over square root of number of times you've chosen that arm. This is your bonus, which encourages you to take the actions that you haven't taken very many times. And so uncertainties or standard deviation goes as 1 over square root of number of experiments or number of samples. So this is, you can think of this factor here as standard deviation of action A times some very slow growing factor, which turns out to be necessary to get the optimal bounds. So the general principle, the general takeaway, without getting into all of the bounds precisely, is you want to choose the arm that maximizes mean return plus the standard deviation of the return times some very slow growing factor, which makes it so you get the optimal bounds. And one way to interpret this is you choose the arm with the best returns if we're a bit optimistic about the value of each arm. And here, optimistic means for each arm, there's a distribution over possible mean values it might have. And you can, being optimistic would be like saying, I'm going to assume it's the 90th percentile value. So, whereas pessimistic would be like the 10th percentile. And medium would be if you just choose the mean itself. And yeah, you're favoring high expected return and high variance. And when you do this, you get logarithmic regret, which is optimal, meaning as opposed to some of these naive strategies where the regret goes up linearly, here the regret or the cumulative suboptimality goes up as logarithm of number of time steps, which is, I think it's pretty remarkable that, well, I don't know, it's not that surprising when you think about it, but. Okay, so that's one pretty important class of algorithms. Another is called posterior sampling or probability matching. So the general principle here is you pull the lever with the probability that it's optimal. And one way to do this in practice, which is usually called Thompson sampling or posterior sampling, is you first sample from the posterior distribution a set of all possible, a set of all your parameters. So let's say we're uncertain about all these different mean values, so we pick a particular sample from the posterior distribution, from our joint posterior of all these values. And then we choose the best action according to that sample. So this is something that we can actually, this is something we can do in practice pretty generally. Because if we have any scheme for computing a posterior distribution over models, then we can get a sample from that posterior and then assume that sample is correct, or assume our that model is correct and use that to choose the optimal action. So I think this is a pretty nice idea. It can be applied really generally. Unfortunately, it has one, well, at least one flaw when you try to apply it to a real setting. So this is a nice nice illustration that Jen Leike told me. So let's say I'm going to use Thompson sampling, where every morning I wake up and I sample a model. So I have a posterior distribution over models of the world. I mean, there are lots of degrees of the freedom of the world that I don't know. So I have this big posterior distribution. And the idea of Thompson sampling is every morning I sample one model from this distribution, and I decide that that's my model for the day, and then I'm going to act optimally according to that model. So let's say I'm also really, let's say I'm very immoral. So I'm going to wake up in the morning, and I'll sample this model, and in this model, there's a certain value of all of your passwords and bank account information and everything. So now I just sampled a random value of all your passwords and bank account information. So I can just now transfer all your money to me because I think I know your password and everything. So then I go and type in your password, like SZ3496, blah, 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 and then it's wrong. So when you do Thompson sampling, it doesn't account, it assumes that it makes all degrees of freedom of the world get set to certain values, which are usually wrong. And what you really want to do is sort of something where you maybe sample some of the more coarse degrees of freedom of the world, but you keep some uncertainty about the more fine degrees of freedom. You can come up with examples where you can come up with smaller examples where you can show that Thompson sampling gives a sort of suboptimal behavior. In fact, so the next slide describes another idea, but this paper, Learning to Optimize via Information-Directed Sampling, they have a nice example, which they have this nice example called sparse linear bandits, where they show that Thompson sampling does something dumb, but their algorithm does something smarter. So if you're interested, check out that paper. So here's another sort of general method for looking at bandit problems. And so the idea here is to think about information gain. So when I described the exploration-exploitation problem before, I said, is something, OK. Oh, new marker, OK. So I said you're making a trade-off between gathering information and maximizing your reward with what you already know. Can we achieve this balance by explicitly providing a bonus for gaining information? So that's the idea behind another class of methods. And there's a general idea. Well, there's this general kind of traditional topic of Bayesian experiment design, where you're deciding, you get to make certain measurements of the system, like you get to do certain scientific experiments, and you want to choose the optimal sequence of experiments to gain as much information as possible. So a very well-known class of methods here is to look at the mutual information between the observation and the parameter of interest that you're trying to gain information about. So let's say, let's call y our next observation, and let's say theta is some latent variable that we're trying to gain information about. So what we're going to try to maximize is this information theoretic quantity called the mutual information. So the mutual information can be written as the expected change in the entropy of the distribution. So it's entropy of our latent variable before our measurement minus entropy of our latent variable after the measurement, and expectation over all measurements of that. And that's equal to the entropy of our actual outcome minus entropy of outcome given our underlying latent variable. But this is the one that we're actually going to measure in practice. So we're going to have a certain uncertainty over our parameter before we do the measurement, and then we're going to have another uncertainty afterwards. This mutual information is always positive, though the thing inside the expectation isn't always positive. Our entropy might go up. So this is something that you can define without consideration of any kind of action. But what we're going to do is we're going to choose actions that lead to high mutual information. So we want to maximize over actions the mutual information given that we take that action. Okay, so there's a bandit algorithm that was proposed by Rousseau and Van Rooij called information-directed sampling. And what it ends up doing is it constructs this ratio. It turns out that the right thing to do is to look at the expectation of the suboptimality squared, where suboptimality means how, according to your mean rewards of all the actions, how suboptimal is your current distribution, your current probability distribution over actions. So you minimize expectation of suboptimality squared over expectation of information gain. Okay. So now I'll just briefly describe this contextual bandit setting, though I won't go into it much, but it's worth knowing about. So here, the environment is not stateful, so meaning each time step, the environment, the distribution of outcomes as a function of your action does not depend on anything that you did in the past or anything that happened in the past. As opposed, in contrast to an MDP where you have the state of a system which evolves over time. So your current, the outcome now depends on your actions in the past and your states in the past. So here, every time step we get a context, and the reward follows this distribution, probability of reward given context and the action you took. So yeah, this is so you have this kind of problem, and now your action should depend on the context, of course. Oh, let's see, I meant to get rid of that slide. Anyway, this is a slightly more general setting where you can study exploration. But let's actually move into MDPs. So here the problem gets quite a bit harder because now you have to you might have to take a sequence of actions to get to the part of state space where you're going to learn something new. So in the bandit problem, you just have to make a decision each time step to try to choose an action that'll gain you some information. Whereas in the MDP problem, there's like an added dimension of difficulty because you also have to navigate through this MDP to get to the states where you're going to gain information. So people have thought a bit about how you can even define what it means to behave optimally in an unknown MDP. So the problem here is your agent is in a previously unknown MDP, so you get stuck in this MDP, and now you need to somehow behave you have to behave in this MDP and learn an optimal policy over time. So this seems pretty hard because you have to both learn about the MDP, learn the parameters of the MDP, and you also have to try to exploit it to get as much reward as possible. So we talked about Q-learning in an earlier class, which we said eventually converges to the optimal policy. However, we didn't say anything about how long it takes to converge. And it turns out it sometimes takes really, really long to converge. And it converges really, really slowly. So the question here is, given a previously unknown MDP, can we converge to the optimal policy, or a near optimal policy, in a reasonable amount of time? That's the question we're trying to answer here. So people have come up with different ways of defining this problem more precisely, what it means to be near optimal in a finite amount of time, or to quantify the sample complexity of an algorithm. So one version of this was proposed by Kearns and Singh, where they said they look at how long it takes to get, how many time steps it takes until your policy is epsilon suboptimal, meaning the expected return of your policy is epsilon from the optimal policy with some high probability, 1 minus delta. So there are two parameters, and you want an algorithm such that with high probability, it's epsilon suboptimal as fast as possible. Question? Yeah.
Yeah. So is the extent to which the MDP is unknown basically you interact with it in like a episodic way?
Yeah. Okay. So that's a good question. The question is, what does it mean that the MDP is unknown, and how do you interact with it? So there are different problem settings where you have different kinds of interaction with the MDP. So actually, that's something that Sham Kakade talks about in his thesis pretty nicely. So he points out that there are actually a few different settings that people consider in reinforcement learning. So one setting is all you get to do is take actions in the environment, and you get to see the states and rewards, or observations and rewards in a POMDP. You don't ever get to reset yourself to a certain state, or you don't have any control other than choosing your next action. So that's one setting. That's sort of the purest version of the problem in terms of most real world like. Then there are other settings where you can put yourself in an arbitrary state of the MDP and, for example, try out lots of different actions from that state. If you have a simulator, for example, you can do that, like if you have a computer simulation of your system. And then there are other settings that are in between where, for example, you can reset your state, but you can't put yourself in an arbitrary place. So yeah, that's a pretty important distinction, and that'll probably affect all of the results. Let's assume for now that we're in the setting where you can't do do anything other than choose an action. So that's the only way the agent interacts with the environment, is to choose an action at every time step. And the environment starts out being unknown, and you may or may not have a prior distribution over possible environments. Does that answer the question?
Yeah. Just to follow up, so you mentioned like you can think about a bandit problem as a POMDP, and I guess just canonically, if somebody said you would think learning a POMDP would be harder than learning an MDP. Is it just because the bandit problem is a very specific type of POMDP that like learning the MDP is harder than the bandit problem? Because I just generally would think that like learning a POMDP would be harder at like first pass.
So is your question, why do we want to rewrite it as a POMDP?
Yeah, was that just like a comment?
Okay.
That you can write it as a POMDP because.
Oh yeah. Okay. So the question is, so was it just sort of a theoretical observation that you can write down the bandit problem as a POMDP, or does this actually have some kind of application? Is that
yeah.
okay? So, yeah, that's a good question. I think it's not, well, I'll talk about later about a way of actually making that observation a little bit more practical, or at least one recent line of work to make that observation more practical. I think it's not totally, it's not just a theoretical construction, because let's say you have to solve a series of different bandit problems where you have unknown parameters. Then you could optimize your policy for solving these bandit problems. So for example, let's say you learn to play lots of different sports, where initially you don't know the rules of the sport, and you just learn it as someone tells you how you're doing, like whether you're winning or not. So as you do this, so you go to this, let's say you go to some contest where you have to learn how to play games without being told the rules. Then eventually you'll get better at this process of like exploring a new game, and trying to figure out the rules as you go along. So in that way, you're kind of taking this unknown problem and turning it into a POM-DP. So it's like you have an unknown MDP, and you're turning it into a POM-DP. So I'll make that I'll talk about that more a little later. Okay, so there. Let's see. So I'll talk. There are various different ways of actually. Okay, so I just described what it means to have a near optimal policy for identifying and solving an unknown MDP. So what kind of algorithms can actually do this? I mean, there's a bunch. People have proposed a bunch of algorithms in the literature that actually are guaranteed to do this in polynomial time, or guaranteed to satisfy the two definitions from the previous. Let's see. Okay, so let me just say on this slide, so we have a couple of different definitions of what it means to solve the MDP, solve a previously unknown MDP. So you could say it takes a certain amount of time to until your policy is epsilon suboptimal. One problem with that one downside of that formulation is it sort of makes a distinction between training and evaluation. So the way to actually check this in practice would be you periodically evaluate the policy you've learned and see if it's near optimal. So a formulation by Kakade is that you look at how many time steps the policy takes a epsilon suboptimal action. So that way you can just the policy starts off taking random actions which are suboptimal everywhere, but over time it gets more and more optimal, and the hope is that after a finite amount of time, the policy only makes a finite number of mistakes. After a certain amount of time, it chooses all the right actions. Okay, so that's just to sort of formalize this idea of what it means to talk about sample complexity of reinforcement learning algorithms. So there are a bunch of different algorithms that are able to learn in previously unknown MDPs and have efficiency guarantees, unlike, for example, Watkins Q-learning. So one class of algorithm is based on optimism, just like we saw in the bandit setting. And here, the way most of these algorithms work by they have an initial model of the world which is optimistic, meaning it assumes that if there are state action pairs that you haven't taken very often, it assumes that something really good is going to happen when you take that state action, when you take that action at that state. So that way, that incentivizes the agent to take all of the actions, to reach all the states and take all of the actions enough times that it can properly identify the values of all these state action pairs. So I think so. So Rmax is one of the earlier versions of this idea. And a sort of simpler version was provided in this nice paper by Sitta and Lorenz, where you initially assume that every state action pair has a deterministic transition to the Garden of Eden state, where you get maximal reward for all future time steps. So it's like you construct this augmented MDP that has this Garden of Eden state, and you initialize your model so that all state action pairs transition to that state with high probability, and then over time you realize that that transition probability gets driven down to 0. So because you take the state action pair and you don't end up in the Garden of Eden state, so gradually the probability of that transition goes down to 0, and you start taking the actions that actually have the highest returns. So this is called the optimistic initial model idea. There's another idea, mostly more heuristic, called optimistic initial value, which is that you have a value function, such as usually a Q function, and you initialize your Q values with some large positive value. And that way, when you visit a state action pair for the first time, or when you visit a state for the first time and there's some action you haven't taken yet, you think that action is really good. And over time, the action value gets driven down. So that's one general class of methods, which is mostly heuristic, and it's sort of inspired by the optimistic initial model methods, but it's more computationally tractable. So with these, by the way, for this kind of method, such as RMAX and also this method I've referenced here, what you do is you have a certain estimate of your model, and you solve for the optimal action, assuming that model is correct. So every time step, you actually have to fully solve the MDP. So numerically, you'd have to fully run policy iteration or something like that to compute the optimal action. And then you update your model, and so on. So these methods are not very computationally efficient because they have to solve the full MDP at every time step, but it's just sort of a construction, a theoretical construction to try to get the best possible sample complexity. Okay, so yeah, the optimistic initial value methods are a way of trying to get at the same idea, but with better computational efficiency. Actually, there's one method that that's in this class of optimistic initial value methods, but it seems to have a theoretical backing called delayed Q-learning. So the idea here is, or delayed Q-learning with interval estimation. The idea is that you add some bonus to the Q values when you haven't taken them in a while, or you continually add some small bonus to the Q values, and that encourages you to take every action occasionally. So you don't necessarily have to do epsilon greedy. It's sort of a possibly better way of doing epsilon greedy, which gives you a better convergence rate. And so it ends up being converging in polynomial time and also being more sample efficient than some of the other algorithms that require solving for the optimal policy all the time. So this is from this Strel paper, where you can find some more details. So now I just want to show a few examples of MDPs. So you can have a sort of mental model of what are some of the hard exploration problems that you run into in the MDP setting, which will give some motivation for the methods we're going to talk about. Because now we're going to start talking about methods that are just heuristically motivated. So one example is called, so one sort of toy MDP, which is illustrative, is what's sometimes called the key, something, I don't remember exactly what it's called, something with key. So the idea, this is a deterministic MDP, and so you can choose to, there are two actions, A and B. So if you choose action A, you move to the right, and if you choose action B, you go all the way back to state 1. So if you initialize with a random policy, it's pretty unlikely that you'll make it all the way to the right, because if you choose action B once, you'll go all the way back to the start. So if you, let's say we can parameterize this MDP by the number of states. And in this MDP, the amount of time it'll take to even get to this last state is exponential in the number of states. And the reward is 1 if you're at this state and you go to the right. And it's 0 at all the states in the middle, and it's 0.2 if you're all the way on the left and you choose to go to the left. So basically, you want to be all the way on the right, and then you'll get reward of 1 if you keep taking this action. But you only, you're not even going to reach this state if you start off with a random policy, or even if you have epsilon greedy. And if you have a large number of states, you're going to choose the random action with probability epsilon, and that's going to send you all the way back. So you're going to have exponential complexity. But in this MDP, any method that favors reaching novel states is going to tell you to go all the way to the right. So if you have any method that gives you a bonus for reaching a new state, it's going to incentivize you to find your way all the way over here to the right. Okay, let's see. I won't go into this one right now. So here's in the continuous control problems like humanoid locomotion, it's actually not so obvious how to talk about exploration in state space, because state space is this high-dimensional continuous space, and not all states are even reachable. So it's not clear. It's not clear how you should explore here, because you can't even reach all of the possible the possible states in the state space. But what happens in practice is that there are local minima in policy space. So what you kind of want is a method you want an exploration method that won't get stuck in a local minimum in policy space. So for example, two local minima you run into a lot are one is where you just lunge forward. Let's say you set up a reward function where you get a reward for moving forward, but you get a penalty for falling over. Then what you might end up with is you end up with a policy that just lunges forward to get as much reward as possible for the forward reward, and then it assumes. Then it's going to lose out on the falling over reward, but if you just start out, you're going to fall over anyway. So that's one kind of local minimum you get, and the other is you just stand still and don't even bother to move forward, because it's hard to successfully move forward and stay balanced. So if you try on your homework, there's a bonus question, which is to do this 2D hopper problem. You're likely to see this kind of behavior, especially if you were to just try tweaking the reward function to see. Like if you were trying to design the MDP, you would have to weigh two kinds of coefficients, where one of them tells you to go forward as fast as possible, and the other tells you not to fall over. So as you're tuning these coefficients, you would find that that you often get stuck in one of these two local minima, where either you're lunging forward as fast as possible, lunging forward and then falling over and then giving up on trying to stay balanced, or you're just standing still and not bothering trying to move forward. And you're likely to see those also if you have, like your hyperparameters aren't exactly right. Oh, and actually, I wanted to show this toy MDP as an illustration, as sort of a toy illustration of the locomotion problem from the next slide. So a very general problem with policy gradient methods is that there's the optimal behavior requires you to go through some advanced part of state space, where that part of state space is bad if you have a unskilled, if you have a bad policy, but if you have a really good policy, then that's going to give you your maximal reward. So for example, dynamically moving forward or dynamically running, you're off balance. Like to be running, when you're running, you're never fully balanced. But running only works if you have a good enough policy to stay balanced. The part of state space in which you're off balance is kind of the advanced part of state space. Whereas if I'm just standing still with my center of mass between my legs, then I'm just balanced, even if I'm standing totally still. So this is like the easy part of state space. And what happens if you run policy gradient methods is often they deplete the probability of being in the advanced part of state space, and they never learn what to do there. So this example is an illustration. It's another deterministic MDP where you can, where the boxes here are states and the edges are arrows. I mean, the arrows are actions you can take from those states. So let's say you start off at this state, and then you can either go right to the done state and get a reward of 0, or you can go over here to this other extra state called B, and from B, you can either go to the done state and receive a reward of 1, or you can also go to the done state and receive a reward of -999. Well, this seems like a pretty stupid MDP because obviously you would take the reward of 1 instead of -999. But let's say you initialize your policy to have 0.5 probability everywhere, to have uniform action probabilities everywhere, as you usually initialize it. Then what's going to happen is, first, when you start learning, it's going to deplete the probability of B practically down to 0, because whenever you get to this state, something bad happens, because half the time you take this -999 reward, and you get so basically initially the value of B is -499.5. So what's going to happen is you first deplete the probability of B down to 0. Then your policy is never going there, so it's never going to learn what to do there. And it's just going to be going here. And what happens if you're lucky, or if you run your algorithm for long enough, is it'll probably start going to B, and eventually it will have gone to B enough times that it learns that you should take this edge that has reward 1, and then you can learn properly that at the start state you should go over to B. But that might take an extremely long amount of time. And actually, it's not even clear if under normal policy gradients you'll converge to the right thing in a finite amount of time. So this is kind of this is a toy problem that captures this aspect of the locomotion problem, because it's like the state B is like dynamically running. It's really bad unless you're doing the right thing there. So you're more likely, if you're not careful, you're likely to just stick to the easy state of just standing still and not bothering trying to move. This actually isn't necessarily about exploration, or at least this isn't about the notion of exploration that's usually discussed in reinforcement learning, which is how to make sure that you reach all the states enough times. This is more about a certain kind of algorithm, policy grading algorithms, getting stuck in local optima or plateau of behavior, but I think they're connected at some level. Oh yeah, and here, actually you run into something similar in the game of Breakout. So if you, I don't know if you tried Breakout with Q-learning or with, you could also try it with the policy gradient implementation from your current homework. It should be able to work reasonably well if you run it on the Atari games. If you take the card pull solver code and you just put in an Atari game and you change the neural net, it actually works okay. I mean, I tried it while I was preparing the homework. So if you run a policy gradient method on Breakout, what you often find is that the paddle goes all the way to one side because the ball shoots out. It shoots out diagonally. So if you go all the way to the left, then the ball will shoot out and you'll get one return. You'll get to return it once, and then you'll lose the next one, or it'll go into the goal. It'll bounce off your paddle, go back up, and then you'll lose it. but at least you get 1 point. So what happens is your policy learns to just go to the corner all the time and receive 1 point per life. Okay, so now, any questions before I move on to deep reinforcement learning?
Could initialization or kind of adding some cost on, staying still help you overcome the problem of getting the launch forward or sitting still?
Yeah, so the question is, could some kind of initialization or some kind of reward for reaching new states, is that what you had in mind? Could that help you on these problems? Yeah, so something like that could help, though it's hard to come up with something that works generally. So I'm going to talk about some possibilities in the next few slides. Okay, so some of the algorithms for optimally solving our discrete MDPs assume that you can take your current estimate of everything and plan optimally according to that. So you can't necessarily do this in the deep RL setting where you have the infinite or large state and action space. You can't plan optimally according to some learned model. And the other issue is that if you have an infinite state space or a very large finite state space, you never reach the same state twice. So you can't do anything that involves counting. You have to somehow generalize between states or define some notion of novelty or like the density of the states you've reached so far. So there are a few different methods, exploration methods that can be extended to the deep RL setting where we have function approximation and where we have large state and action spaces. So one idea is to use posterior sampling, which naturally generalizes or extends to this setting. So the idea, there are several versions of this idea. One version is that you have a distribution over value functions. And so that's like, you can, I mean, what we would like to do is have a distribution over models and plan optimally according to one of those models. Or at least that's the method that's closer to some of the methods that have, from the finite MDP case, that have some theoretical guarantees. But another approach is to have a distribution over value functions. And in particular, there's a paper by Osband and others. Let's see. Oh, yeah. There's a paper by Osband and Van Roy that describes this idea. Actually, I might have cited the wrong. Did I cite the wrong paper? It's Osband and others. Osband has a couple papers, so you can find his papers on arXiv. So the idea is that you want to have a distribution over Q functions, and each episode you're going to choose one of those Q functions and choose greedy actions according to that Q function. So this is like in Thompson sampling. You wake up every morning, you choose you sample one possible state of the universe, and you act according to that state of the universe. You act assuming that that's correct. So the way the authors do it in that paper is they apply this in the Atari setting where you have a convnet that takes in the game images and outputs Q values. So you have some layers of the Q function, and what they do is they create multiple heads of the Q function, which means there are several layers of the Q function that are where they have multiple copies of these layers, which are going to learn differently. They're going to be trained to give different Q functions. So in particular, there's this method in classical or frequentist statistics called bootstrapping, where you resample your data set and you fit your model to different resamplings of your data set. And if you take your ensemble of models that you get that way, this ensemble will give you a distribution of outputs for any input you put in. And that way you have an you can get uncertainty estimates on all the outputs of your models, because now you have an ensemble of different models. So so they want to apply this idea for Q-learning because the bootstrapping gives you a reasonable distribution over models. So what they do is they have this multi-headed Q function where the last couple layers are not shared between a bunch of different, are copied a bunch of times, and you fit each of these Q function heads to different subsets of the data, or different reweightings of your data. So that way, all of the each head is a different Q function, and you can and each one will give you a different greedy policy. So every episode, they choose a different head and use the greedy policy from that head to define to choose actions. There's also a nice paper by Gal and Garamani, which is not in the RL setting, but they have a nice discussion of using bootstrapping on deep neural networks to get uncertainty estimates. So, and they say how you can use it, for example, in classification to see if your model is overconfident about classes of unseen data. And there's another nice paper by Lipton and others where they use Bayesian neural networks instead of bootstrapping. So bootstrapping is one way to get a distribution over models. Another way is Bayesian neural networks, where instead of having a single neural network, or instead of having explicitly an ensemble like this, where you have k copies of your network, the idea of Bayesian neural networks is you have a mean and a standard deviation over each parameter. So that way, so you're basically saying that your posterior distribution is a Gaussian distribution. And actually, it's not that clear how you should actually incorporate evidence in this framework. So it doesn't totally. I don't think it's totally worked out exactly how you should do Bayesian Q-learning. Because normally when we use Bayesian neural networks, we're using the variational lower bound, which is a lower bound on log probability. But here it's not clear that we have that there's really. We're not fitting a Q function using some likelihood. It's not really a likelihood. So it's not clear exactly how to do this in a fully Bayesian way. Okay, so that's one class of approaches, posterior sampling. Another approach that people have looked at is to provide an exploration bonus for visiting states that haven't been visited very much. There's several. So the hard part here is now let's say you've got an infinite state space, like you've got images from a game, or you've got like the robot joint angles. How do you decide how novel this image is or this robot state is? Well, you can try to fit some kind of density model. That's one thing you could do, but it's not clear if your density model is going to focus on the right degrees of freedom or the wrong degrees of freedom. So let's say I'm wearing a wristwatch, and we count that as part of my state. Then I'm always in a new state. So the density is 0 at every state because my wristwatch is always, or actually I guess it has to have a date on it also. Basically, you can set up the problem so that the density is always 0 in the new state. And what you really want is to focus on the, using a density model isn't the whole story because you want to focus on the interesting aspects of the state or the relevant aspects of the state. So one idea is that you should try to figure out how novel the state is by how well you can make certain predictions of some kind of side task. So one idea was you try to do next state predictions. So you try to predict the next observation or the next some kind of auto-encoded version of this, or some kind of compressed version of the next state. If you're in a part of state space that's very familiar and well learned, then you should be able to do this next state prediction very well. So the idea from this paper by Stady and others was to provide a bonus based on your prediction error. Does anyone see one possible like flaw in this, or some kind of pathological, or can you design an MDP that would cause this to do the wrong thing? If you're providing an exploration bonus based on prediction error. Mm-hmm.
If you have something that's very random and not very good, but just a huge distribution of the whole thing, the exploration bonus for that would never go away.
So if you have a system that's stochastic, then the exploration bonus will never go away. Like if there's just stochasticity in the system. So can you think of where this would do the wrong thing, like where it would like actively go to the wrong parts of state space? Well, let's say we add some, okay, yeah, so that's a good point also. Like maybe the right thing is you need to stop exploring at some point. So you don't, so if you do this prediction error thing, if you use prediction error, then maybe it'll never go down because your system is stochastic, so you'll keep exploring. But let's say we put 1 over square root of n, we put a 1 over square root of n factor in so that it dies down over time. Is there still any kind of problem? Like, does this always measure novelty? Or can you construct an MDP where this doesn't necessarily correspond to the novelty of a state? Like the prediction error doesn't necessarily have anything to do with novelty.
Well, maybe this pathological example, maybe there's like some action you take and like some bomb explodes. You can't predict what happens. You just have like essentially random static observation, but it looks novel.
Yeah, so that's exactly what I had in mind. So the idea was maybe you have some action that causes a bomb to explode or something crazy to happen, which is really random. So yeah, I think one issue with this, or one possible failure case, is that you might have a part of your state space where there's high stochasticity in your observations or in your transitions. So this will bias you to moving towards parts of your state space where things are unpredictable, even if those parts of state space are extremely well identified and you're extremely familiar with them. So, I mean, certain things are just are random, and so one way to illustrate this is, let's say you have a TV that's showing static, and that's off in the corner of the room somewhere. So if you use this kind of exploration bonus, then you're incentivized to go and sit right in front of that noisy TV, and just you'll keep receiving maximal bonus for prediction error. Yeah, that's one possible issue with it. So one way to address this is to actually look at information gain instead of prediction error. So that's what this paper tries to do, variational information maximizing exploration. So the authors use a distribution over models, over dynamics models of the system, and provide a reward if there's an update to that distribution, so if information is gained. And that's not susceptible to the noisy TV problem, because eventually you'll perfectly identify the model of the noisy TV and the distribution of static it's going to show you, and you won't be updating your model anymore. In practice, it's pretty hard because you have you have to normalize things in a way that you keep getting exploration bonus. So you're not actually doing Bayesian updates. If you're trying to use a Bayesian neural network, you have to use lots of approximations, which make this a little bit harder. But that's one approach. Another approach is there are these two papers that try to actually fit a density model. and use that to define an exploration bonus. So we have these theoretically justified methods that are, count how many times you visited each state, and some of these methods have nice theoretical guarantees. So the idea in these two papers is to actually learn a density model and use that to provide an exploration bonus in some way that's motivated by trying to make the trying to compute some quantity based on your density model that behaves like a count. That behaves, so they call it a pseudo count, and they use the pseudo count to define a bonus. So you can look at those papers for more details. Another approach is to take this idea seriously that you should look at the unknown MDP as a POMDP. So you should consider, so the way you can set it up to be a little bit more precise is you say that there are inner episodes and outer episodes. So each inner episode, so you have this inner MDP where, well, this is just a normal MDP. And you have an outer MDP, or an outer, where you sample a random MDP and you act in that MDP for, let's say, 10 episodes. So the outer MDP well, actually it's a POMDP. So you have this outer POMDP where you get a random inner MDP and you perform 10 episodes in that inner MDP. So that way, the optimal policy for the outer POMDP is to first explore in the first episode and try to gain as much information as possible and then exploit it in the later episodes. So by sampling your inner MDP from some distribution, you can actually learn the policy that behaves optimally. So here we're really taking the idea seriously that you should look at this this problem where you have an unknown MDP as just this is itself a POMDP, where you're identifying, where you're looking, your belief state is getting updated over time. So you can use a recurrent neural network policy where you don't reset the state in between, like at the boundaries of the inner episodes. And this MDP receives the reward in addition to the observation and the actions. Whereas usually when people use RNN policies, they don't pass in the reward. But here, by passing in the reward, you can ensure that it's actually implementing, well, it's actually identifying the system over the first few trials of the inner MDP. Okay, there's also another idea called, we're running out of time, but this is the last couple of slides. So there's this idea of intrinsic motivation, which is actually, well, it's not that formal of an idea, but it's generally, you want the learning process for an agent to proceed well. So we want to design reward functions that cause it to do the right thing if it's behaving in a system for a very long period of time. So even if you're getting sparse rewards, or even if there's certain, even if the agent can, for example, get stuck in a sync state. So basically the intrinsic motivation or intrinsic rewards are just reward functions that are assumed to be not the thing you're actually trying to optimize with the agent, but something that benefits the learning process. So for example, to ensure that the agent explores and learns, learns the system, or to ensure that it remains safe and doesn't, for example, die. So there's been some papers on that. And exploration is sort of one kind of intrinsic reward. Or exploration bonuses are one kind of intrinsic reward. But intrinsic rewards aren't specific to providing bonuses for reaching novel states. They can also try to make the agent more conservative to avoid novel states. But there have been some nice papers on this. Well, there's some more classic papers about this idea And there have been some recent papers about that explore different kinds of intrinsic motivation, including exploration. But exploration is sort of one kind of intrinsic reward, or exploration bonuses are one kind of intrinsic reward. All right, that's it for today. Thank you.
So in a kind of thermodynamic sense, the prediction-based thing is actually the worst thing you can do, right? Because